Good afternoon, students.
Good afternoon, ma'am.
How many Ajinkya in this class? One or two? Ajinkya Pale? Any more Ajinkya in this class? Ajinkya, your mic is not working. I'm asking about Ajinkya because suddenly this reminded me of an old experience of mine in class. I was teaching machine design 1 to, then it was in 5th semester. MD1 was in 5th semester and MD2 was in 6th semester or 7th semester, I guess. And there was this boy named Ajinkya, and he was probably Gujarati, and he was not interested in engineering at all. The moment, but he used to have 100% attendance. He used to come in the class, sit somewhere in the last bench, and then he used to sleep. Now imagine in physical mode, if you are continuously sleeping in the class, you are bound to get attention of the teacher or the class. Every class he used to sleep. And after first, second, third, fourth, fifth lecture, I probably asked him, why do you sleep? Are you on some medication, on some drugs? And he said, no, I'm perfectly all right. Again, next day he was sleeping. Again, next day he was sleeping. Then one day I asked him, come and sit on the first bench, so you won't sleep. He said, ma'am, please let me sit on the last bench. I promise I'll not sleep. I said, okay, because you're promising. I respect your promise. And he was sitting, he was wide awake, and he was continuously writing. And to my utter surprise, how come he is fully awake and he's writing? So I just thought of roaming in the class and see what he is exactly doing, what exactly he is writing. Because he was not looking at the board and he was continuously writing. And then I saw he was drawing something. He was probably doing some kind of sketching, and he was sketching a cartoon story, like in blocks. So there was first block, second, third, fourth, and then the entire block would complete a story. Because you are in the middle of a problem, I thought not to disturb the entire class, because then everybody in the class wants such kind of disturbance. They also need a break, a commercial break kind of thing. In my second, third round, after 15 minutes, I thought of snatching whatever he was drawing in that class. But as teachers, we are also worried. I don't know what he might be drawing. I was not very sure whether he is creating some story with me there as a central character or a negative character. And should I snatch or should I not? But after 15-20 minutes, I just snatched that paper and I asked him, what is that he is doing? What is that he is drawing? And there was some kind of story, some cartoon story. And I asked him, what are you doing this, Ajinkya, in the class? And he stood up and with full confidence, he said, ma'am, at least I am awake. You should be happy about this. So look at the confidence of the student. At least he was awake. So he said, you can keep that with you, but you should be happy that at least I am awake. And then he came to my cabin and I asked him, what's the problem with you, Ajinkya? Either you are sleeping or if you are awake, you are doing some stuff like this. He said, ma'am, I'm not interested in engineering. My father wanted me to become an engineer, but he himself is a businessman. My mother is, she's an artist. Even I am more interested in arts, in drawing, in sketching, and painting. This engineering is not my cup of tea. I'll be here for next 4 years. Somehow I'm going to clear this, get my degree, give it to my father. See, now your son is an engineer. Now you can boast that your son is an engineer, and then let me live my life my way. That was his sad story. Well, coming back to whatever we were discussing, 73 is a good number. Okay. We started about this worm and worm wheel, which is normally used in cranes and hoist. And this is how a worm and worm wheel looks like. And we are going to design this from the strength consideration and from this heat dissipation point of view. We discussed about 3 different types of worm and worm wheel assembly with no envelope, single enveloping and double enveloping, and how the stresses are maximum and so the power transmission capacity is limited in the first case, and in the third one, because it's an area contact, stresses are less, so the power transmission capacity increases. But the limitation is mounting is very difficult. It has to be very precise. So then we discussed about the terminologies that we are going to use in worm and worm wheel design. So here this is a worm, and for the screw thread here, this is the lead angle, this is the axial pitch, and this is the circular pitch. And for the worm to mesh with a worm wheel or a gear, this axial pitch must be equal to the circular pitch. And then lead is the distance traveled in one full revolution or one full rotation of the screw thread. This gives a lead angle tan of lambda as the lead value upon pi dw, where dw is the diameter of the worm. Now, worm and wheel, they are rotating in about 2 mutually perpendicular axes. So whatever happens to be the tangential force for gear becomes the axial force for the wheel, and the tangential for the wheel becomes axial for the worm. That is because of their axes which are mutually perpendicular to each other. And then there's a radial force which remains the same for both gear and wheel. We are using small g as subscript for gear or wheel and small w as subscript for worm. So this is axial force for gear and this is tangential force for wheel. Tangential for gear and axial for worm, and the radial for both remains the same because this would be the radial force in this plane. Similarly, here in this plane, this would be the radial force, which will remain the same. Then we discussed about the term diametral quotient and how the designation of worm wheel is, or the worm wheel and worm gear is given, which takes into consideration number of threads on worm, which is also the number of starts of worm, number of teeth in the gear, Q, which is the diametral quotient. It is the ratio of diameter of wheel and module of the gear, and M is the module of the gear. I hope your design data book is handy. We'll quickly go through the design data book first, and then we'll go with few more derivations for the magnitude of axial, radial, and tangential forces, efficiency, and the rubbing velocity. Please open page number 175, table 1615. Design data book, B.D. Shivalkar. Design data book, as per my page, it is page 175, table 1615. Design formula for worm gears. What is the design power given? Start posting on the chat group, please. What is the design power PD given in watts? PR into K1, where K1 is the load factor and the value of load factor is given in table 11.5. So that we'll refer later. Next is tooth load, FT, or the static load. And what is the formula given? PD by VP. So PD is the design power and VP is the pitch line velocity for the gear as usual. Next is the beam strength, again given by the same formula S0 CV By into M, where the value for CV by calculation would be, what is given over there? What is the value or the formula for VP given? 6 upon 6 plus VP. Now, if you remember in spur gear and helical gear, we had 3-4 different formulas for CV depending upon the velocity. Now here, this gear will always be rotating at comparatively low velocities. Worm will be rotating at a higher velocity because worm is the driver and gear is usually the follower or the driven shaft. This will be rotating at comparatively low velocity and the CV value will be 6 upon 6 plus VP. And since VP is not initially known module we are assuming, so we will always take the value of CV as 0.75. Assumed value of CV for initial calculation and later we'll calculate by this formula, where now the value of Y, where Y is a Lewis form factor, this is given in terms of pressure angle, normal pressure angle phi n. What is given over there? Roll number 52, 53, are you there? Roll number 52. Are you there? Sudha, Divakar. 53. Yeah, give me the value for Y. What is given in the data book? It's given as 0.314 into 0.0151 into phi n, which is the normal pressure angle minus 14.5. Value of pressure angle phi n will take from the next table. There's a table given on next page, table 1616. Choice of lead angle and pressure angle. Depending upon the value of lead angle lambda, we'll select what is the pressure angle phi n. For lead angle in the range of 20 to 25 degrees, what is the pressure angle phi n given as? Tanvi, it's given as 22.5 degrees. And how are we going to calculate this lead angle lambda? Only for compact design, we'll be using the formula what is given on the same table. Tan of lambda is cube root of Ng by Nw. But for the value of lead known and diameter of wheel known, we'll be using the formula tan lambda again given in the previous page, which is L upon pi dw, lead upon circumference of the worm. So from here we'll pick up phi n. If lambda value is only 12 degrees, phi n is 14.5 degrees, what would be Y? What would be the Lewis form factor Y? Rishikesh? Roll number 57, Rishikesh. The value will be 0.314 because pi n for lambda 12 is 14.5, so this term becomes 0 and Y will be 0.314. Next is the limiting wear strength, again by the same formula. Next is efficiency of the worm gear. This is given in terms of some angles theta, lambda and mu. This we are going to derive now. And then the formula for heat generated in the worm. Heat is generated in the driver, that is the worm, which is given in watts, and this depends upon the efficiency and the rated power PR. And the heat dissipation will depend upon the specific heat capacity, the heat dissipation area, and the rise in the oil temperature. So this we have seen. So while solving the numericals, we'll check with Q1, we'll find out Q2, we'll equate these two, we'll find out what is the rise in the oil temperature. So the maximum rise that is permissible is 60 to 70 degrees. If it goes beyond that, then we have to modify the design so that the heat dissipation area increases so that del T value goes down. So this we are going to study. Similarly, on the next page, there is a term known as rubbing velocity. Rubbing velocity. This rubbing velocity VR is given, and what is the formula given there? Riddhima? What is the formula for rubbing velocity VR given there in the data book?
It's pi dw nw by cos lambda into 1000.
Correct. And then there is a range of rubbing velocity and then the coefficient of friction mu, which will also be required for calculating efficiency. So for the rubbing velocity in the range 10 to 170 meters per minute, what is the value of mu given over there? Kaustubh? Kaustubh? Kaustubh, are you there with us? Vedant? Vedant Mahore? Either switch on your mic or post in the chat box. It's 0.132 divided by VR raised to 0.28, which means we must calculate VR first, then we get the value of mu, and this mu will be using the formula for efficiency. And then turn a page number 178, table 1619. This is giving you the dimensions for the worm and the gear. Table 1619. This table we'll be using for design of worm. As I said, in this entire design, we'll be designing only the worm wheel or the gear, not the worm. And from these two tables, we'll find out what is the pressure angle, pitch diameter of the worm, face length, depth of the tooth. Similarly for the gear, all these dimensions. So all we have to do is design the wheel, and then we proceed with the selecting the dimensions of the worm from this design data book. So with this design data book, the design would become pretty simple. So assuming how to refer to the design data book, this part is clear. We are moving ahead with few derivations on forces. Now there are so many terms, and this worm and worm wheel is especially complicated because this worm is rotating about an axis which is perpendicular to the axis of rotation of gear. I request you to please be very attentive. The force which is axial here to the wheel, this force, this becomes a tangential force for the worm. Similarly, this tangential force for the gear, its reaction becomes axial force for the worm, and the radial component of the force, they remain the same. So if we are deriving the expression for worm, whatever is FWA, the axial force for the worm, this becomes tangential force for the gear. directions and the nomenclature is different, the magnitude would remain the same. So now we are going to derive the relationship between all these forces. So we are concentrating on the worm, assuming this as the driver. This is the worm rotating on the shaft. These are the worm tooth or teeth. And you can see that you have to draw this figure. You can skip this one. Please draw this figure. This is the radial force on the worm, which is FWR or FRW. This is the axial force coming along the axis, FWA. And this is the tangential force, FWT. So these are the forces. And you see that between the tangential component of the force and the axial component of the force, this is the resultant which is acting at an angle, lambda, which is the lead angle. So if this is the axial force for worm, this is the tangential force for worm. This is the resultant. Let me take this as Fn, which is making an angle lambda, which is the lead angle. And I can write from here, from this figure, what is Fa in terms of Fn and lambda? What is Fa? In terms of Fn and lambda? Yes, please. Fn cos lambda. And what is Ft? Ft is Fn sin lambda. Now there is another force, radial force, and if I take the resultant of this Fn component, which is acting at lambda, or which is the resultant of Fa and Ft with Fr, I get another force component F. So this is Fr. If I add this force F here, this is Fn. Then the angle between Fn and Fr, if I assume this angle as theta, where this theta, it depends upon the lead angle lambda and it depends upon the pressure angle phi n. This force is, say, F. So what is F? F is resultant of Fr and Fn, and Fn is resultant of Ft and Fe. Now everything is with respect to worm. So F is finally the resultant between all these three forces, radial, axial and tangential. So this force F, this is making an angle theta with this n, Fn. We are taking this as theta, don't go with this nomenclature, this would be confusing. And so this Fn is what in terms of F? What is Fr? Fn is F cos theta, and Fr is F sin theta. So I'm trying to combine these two equations. 1, 2, 3, and 4. So let me write everything in terms of F. Fr is same F sin theta. What is Fa? In terms of F, Fa is F cos theta cos lambda and Ft. Ft is F cos theta sin lambda. Is that correct till here? Prajwal? Prajwal, is that correct? Okay.
Yes, ma'am.
Now there is a role of friction coming over here, and as we discussed earlier on, the friction comes into picture only for the worm and worm beam. Because of sliding between the helical thread and the gear tooth, there is this component of friction or mu which comes into role. So if this is the force F here, then opposite to the direction of rotation, if this is the rotation, opposite to the direction of rotation perpendicular to this force along this helix angle, here there is a component called mu F which comes into picture because of this coefficient of friction mu. So if this force F is a resultant of these three forces, axial, radial and tangential, for this force F, there is a frictional component of force which is mu F, and if I resolve this mu F is again acting at an angle lambda with this component of force which is the tangential component of force. So if I resolve this mu alpha again into sine and cos component, you will see that its component, cos component, would be added to this tangential component of force, and its sine component would be along this axial force but in the negative direction. Because of friction, when we consider friction, we get two more component of force. One is mu F sine lambda, and the direction for this is along the axial component of worm but opposite to it. And there is a cos component which is added to the Ft component, same direction. So this formula for Fa and Ft that we have taken, this is without considering friction, but you know that friction comes into role, and so considering friction, now the forces are, what is final value of Ft now and Fa? This is for worm. It is F cos theta cos lambda minus mu F sine lambda. Is that correct? Saurabh? And then there is FA. Sorry, this is FT. FT for worm, which is F cos theta sine lambda plus mu F cos of lambda. FR remains same. FR component is not getting influenced by this friction component. So this FT component on the worm, this is a tangential FT caused by friction, or is it an additional force along with frictional force? It is an additional force. So the total force acting on the worm has two components. One is the normal reaction F, and another is this frictional force component. Mu F. So there is this component cos theta, cos lambda, and cos theta sine lambda coming along the axial and tangential, and then because of the frictional force mu F, there is again mu F sine lambda and cos lambda component. So that is an additional force coming on the worm. Since the value of mu is not considered in case of helical gear, this component does not exist in case of spur gear and helical gear, but here we do consider this. And so for the calculation of the torque, this will be the torque available at the worm upon radius of the worm, or d by 2. And we are not going to calculate this F component also. So now let us write down this FA and FR also in terms of FT, because the power available at the worm will be given in the problem, or the torque will be given, radius of the worm if it is known. Then we know what is FT, and from FT we will be calculating what is FA for the worm. Give me FA in terms of FT, eliminate F. Similarly, give me FR in terms of FT, eliminate F. Give me the values quickly, please. Omkar, Prabhat, give me the answers. Prabhat, you are there? No. Omkar, roll number 77. Not Not there. Prateek? Yeah, Prabhat, give me the value for FR in terms of FT. FR is FT sin theta cos theta sin lambda plus mu cos lambda. And FA in terms of FT is
Cos
into, yes,
cos theta cos lambda minus mu sin lambda by
minus mu sin lambda is
cos theta sin lambda plus mu cos lambda.
Now this formula is not given in the design data book, so you'll have to remember this while solving the problem. Either you remember or you derive it every time. So if you can draw this figure very well, you can derive it easily. And from here, if we want to get the efficiency, we'll need one more term for getting the efficiency, and that is in terms of the rubbing velocity or the relative velocity. So look at this particular figure. If in the side view this is the gear or the wheel, this is the worm. In this view, the gear is looking like a rectangle, and this worm is another rectangle over here. I am using this view because this is the only view where I can show both the velocities. So the velocity of the gear, this is acting in this direction. Say if my gear is rotating like this. So this is my VG component. This is the velocity of the gear acting here. Similarly, now the worm is rotating about this shaft. This is the rotation of the worm. And so perpendicular to this, I can draw the component of velocity here. This will be the component of velocity of the worm along this plane, where this is its axis of rotation. This is the axis of rotation. Axis of the worm is vertical, axis of the gear is horizontal in this side view. So again, the angle between the velocity of direction of velocity of gear and direction of velocity of worm, they will be making an angle lambda with its relative velocity, and this is the sliding velocity lambda. The sliding velocity, or in the design data book, we are using this as rubbing velocity VR. So we'll be using the same terminologies. So what is VR now in terms of VW and lambda? VR is same as VS. So how can I write down VR in terms of VW? Yes, please. VR is velocity of worm upon cos of lambda. And what will be the velocity of the worm in terms of its diameter and its RPM? This will be pi dw nw upon cos lambda. This is exactly what is given in the design data book for rubbing velocity via the last column. This is pi dw nw upon cos lambda into 1000 to get it in meters. So if n is in RPM, diameter is in millimeters. If you want to get this in millimeters per minute, you will multiply this by 1000. This will be in meter per minute. We are not dividing it by 60. You divide it by 60 and you get it in meter per second. So the value for VR in the data book is given in meter per minute for the range of 400 to 1000. It is for precision gears, and if it is less than 400, they are the ordinary gears. From the value of VR that we calculate here, we'll go with what is the coefficient of friction mu, and from mu, we'll find out what is the efficiency. Now, as in case of spur gears, the ratio of their diameters is inversely proportional to ratio of their RPM. This is not true in case of worm and worm wheel. We'll see how it is not true. The RPM for gear and the RPM for the worm, this is inversely proportional to number of teeth on the worm to number of teeth on the gear. This condition holds true, but the pitch circle diameter for the gear upon pitch circle diameter for the worm. Pitch circle diameter for the gear, you know, is module times number of teeth on the gear by the usual formula for the gear. And dW in terms of diametral quotient Q is M into Q. Diametral quotient Q we have defined as dW by M. You can use capital D or small d, whatever. So this, if I am rewriting in term, I am introducing the W term here in numerator and denominator both. Can you tell me what is this Q upon TW? What is this Q upon TW? If you can refer back to the derivations. What is Q upon TW? We derived cot lambda. Yes, that is cot lambda, which we derived in the yesterday's class. And so this ratio happens to be TG by TW this is NW by NG. Q upon TW is cot lambda, or I'm writing this as NW by NG into tan lambda. So this is the relationship between dG by dW in terms of RPM. So ratio of their RPMs is inversely proportional to ratio of their number of teeth, but ratio of their diameters is not proportional to the ratio of their number RPM, but there is a term tan lambda which is coming in picture. So here you have to be very careful when you are taking the ratio of their diameters and ratio of their RPMs. So another term is efficiency of a worm wheel, and by the usual definition of efficiency, it is always the output power upon the input power. power output. We'll complete all these derivations today. So next class we'll solve the numericals upon power input. Now output is at the output shaft, which is carrying the wheel. So it is the tangential force on the gear which is responsible for transmission of power, acting at the radius dg by 2. So this becomes the torque, force into its radius, this is the torque, and torque into the RPM, Tg into 2 pi. So this becomes T omega. You know that power is T into omega. So omega is 2 pi n and torque is the tangential force into the radius upon the power input is the tangential force at the worm acting at the radius of the worm into 2 pi n w. This is the formula for efficiency. In the design data book, it is given in terms of cos theta, tan lambda. So we are trying to simplify this to get that term. So how can I write or simplify this as T or G upon Ft or W? What is this ratio coming out to be? dg by dw into ng by nw. What is this ratio? This is tan lambda. So this is exactly this rewritten. Rearrange. So this is tan lambda. And what is Ft for gear upon Ft for worm? What is Ft for gear upon Ft for worm? Ft for gear is same as Fa for worm. Do you agree? Ft for gear is same as Fa for worm. This is Ft for worm, which we have already derived, into tan lambda. You know what is Fa in terms of Ft. So what is Fa by Ft? This also you know. Give me this. Multiply it with tan lambda and give me the final expression. I just want to see how many of you are actually working. Dhanush, are you there? Dhanush, 83. Harsh Prasad. Harshil. Harshil Shah, you are there?
Yes, miss.
Yeah, give me this expression of efficiency. Aditya, 109. We have two Utkarsh, 112 and 113. Utkarsh, both of you are there.
Yes, ma'am.
Yes, ma'am.
Give me this expression quickly. So Fa for worm upon Ft for worm, we have already derived. This is cos theta sine lambda minus mu sine lambda by cos theta sine lambda plus mu cos lambda multiplied by tan of lambda, which we have simplified as cos theta cos lambda minus mu upon cos theta tan lambda plus mu. Okay. Can you again rearrange to get something like what is given in the design data book? देखो design data book में क्या दिया है? Same thing is rearranged whatever expression is given by Atharva. Is cos theta mu tan lambda upon cos theta tan lambda plus mu. Yes, so this expression is correct. We have to just rewrite in terms of what is given in the design data book, so we understand why the value of efficiency comes out to be like this. This is cos theta minus mu tan lambda upon cos theta plus mu cot lambda. Okay, Atharva, correct it. Where this theta is the angle which the resultant of three forces is making with Ft, and tan of theta is tan of pressure angle in the normal plane into cos lambda. So while we solve the numerical, we'll take the tan lambda first. We'll get the value of lambda. From lambda, we'll get the value of pressure angle phi n. From phi n and lambda, we'll get the value of theta. And from these three values and coefficient of friction, which we'll get from the rubbing velocity Vr, we'll find out what is the efficiency. And from efficiency, we'll find out what is the heat generated and then the heat dissipated. And this entire thing will be doing for design of worm and worm wheel, wherein I told you that worm and worm wheel design is based on the strength and heat dissipation both. Next 2 minutes, let me quickly revise whatever we have discussed till now, because this part is very important. So we'll quickly go through the entire. I forgot to start the recording. Okay, so we started with the discussion on worm and worm wheel, which works for a very high velocity ratio, and it finds its application in lifts, hoists, crane, elevators. The major advantage being we get a large reduction in the speed. This is also acting as a self-locking screw. This is reversible, so it can rotate in both the direction, and so you can lift it up and you can lower it down. At any stage, you can hold your lift in at first floor, second floor, third floor, and by its design, it can self-lock itself. It is silent, it is smooth, and it is compact. So for the same velocity ratio, we'll have to use a series of gear trains or entire gearbox if you go with spur gear or helical gear. But in case of worm and worm wheel, in a small storage space, you can have this huge velocity ratio. So we say it is very compacted design. The disadvantage being we have large friction here because of the sliding action or the rubbing action between the gear tooth and the helical screw, due to which the efficiency becomes low. Higher the velocity ratio, lower is the efficiency, and then there is a problem of heat generation, and hence this always needs to be well lubricated to reduce the efficiency. So we'll be designing it for strength and for heat dissipation both. To reduce the friction, we'll be always using phosphor bronze material for the worm and worm wheel. Then we have seen how we'll work with the heat generated and heat dissipated. And heat generated and heat dissipated depends upon the type of material used, it depends upon the specific heat coefficient, it depends upon the surface area, the oil or the lubricant that is used, and how much temperature it can rise to. All kind of worm and worm wheel are also used in the application where very low speed but high torque is required. So power remains the same. As the speed goes down, the torque increases, and this also finds application in rolling mill. Only one particular model of Audi is using this worm and worm wheel in its differential for transmission of power. These are some of the images of worm and worm wheel. You can easily find it in such kind of toy cranes as well. So in the next class, we'll be working with this heat generated and heat dissipated, and for which the rated power will be calculating using this empirical formula. This formula is based on what is the center distance, accordingly how much rated power this can handle or this can manage. So this is the formula for power only from heat dissipation point of view and heat generation point of view. We discussed about 3 different assemblies of worm and worm wheel with no envelope, single envelope and double envelope, and how the power transmission capacity improves from no envelope to double enveloping gear. Then some basic terms for meshing of worm and worm wheel. The axial pitch of the worm must be same as the circular pitch for the wheel. Because their axes are perpendicular to each other, non-parallel, non-intersecting. The tangential force for the gear becomes axial for the worm and vice versa. So the radial force remains the same. Lambda, this is the lead angle. This tan of lambda is the slope of a triangle whose height is equal to lead, which is the distance traveled by the nut or the screw in one full revolution. So in one revolution, it travels a distance equal to its circumference, which is pi dw. And depending upon how many starts are there, the distance traveled will be 2 times, 3 times or 4 times of its axial pitch. So that part will cover up separately. We introduce a term called diametral quotient, which is the diameter of the worm upon module of the gear. And if we rearrange all these terms, we get tan of lambda as TW by Q. This term we'll be using later again. This is how a worm gear is designated in terms of number of starts of worm, number of teeth on the gear, diametral quotient, and module of the gear. Then we are referring to the design data book, table 1615 and 1619. The assumed value of CV will be used as 0.75 for wheel or the gear, which normally rotates at quite low RPM, normally less than 100 to 200 RPM. Working with the forces acting on the worm, we have seen how the axial force for worm becomes tangential for the gear, and tangential for the gear becomes axial for the worm, and the radial forces remain the same. So for this worm, which is acting as a driver at this given point, if this is the axial force acting on the worm, this is a tangential force, then the resultant of this axial and tangential is acting at an angle lambda. If I take the resultant of this force, Fn, and the radial force, I get another resultant F, which is a resultant of these 3 forces, and this force F is acting at an angle theta. This force F, which is a resultant of all 3 forces, this is acting at an angle theta, and this theta would depend upon lambda and pi n. Now we have resolved this Fn in its horizontal and vertical component. Similarly, this Fn horizontal and vertical component, and we got these expressions without friction, Fr, Fa and Ft in terms of F. But since there is a role of friction also coming in the picture, for this resultant force F, the coefficient of friction mu times F, this force is acting in the direction opposite to the rotation of the worm. and perpendicular to this F, which is again acting at an angle lambda with the tangential force. So we resolve this mu F component also in its sine and cos component, and we have seen that its sine component is acting along the axial force but opposite to it, and its cos component is acting along its tangential force in the same direction. And so the total force on the worm, which is because of its normal reaction and frictional force, we are adding, so considering friction, the value of Fa and Ft for worm comes out, or it's given by this expression in terms of F, theta, lambda and mu. So since the power P is known and this power will generate the torque at the worm, so this torque upon the radius will give the value of Ft. From Ft we will calculate the value of Fa and Fr in terms of theta, lambda and other values given. For finding out the efficiency, we have to use a term rubbing velocity. Rubbing velocity is the relative velocity between the worm and the gear. Since these two components are rotating in two mutually perpendicular directions, non-parallel, non-intersecting shafts, for the gear rotating say in clockwise direction, this is the direction of velocity Vg, and for the worm which is rotating about this axis, I am drawing its side view, where my worm looks like a rectangle and gear also looks like a rectangle. So for the worm, its velocity component is acting in this direction. And their relative velocity again acts at an angle lambda, which is the lead angle. So this relative velocity, which we are calling as rubbing velocity or sliding velocity, this rubbing velocity comes out to be Vw upon cos lambda, where Vw is the linear velocity of the worm given as pi dw nw. This term is used in the design data book. Now ratio of their RPMs is inversely proportional to ratio of their number of teeth, but this is not true with their diameters. So ratio of their diameters we are writing again in terms of module number of teeth and diametral quotient, and we get an expression that dg by dw is inversely proportional to nw ng, and there is a component of tan alpha coming into picture. So efficiency by definition is power output by power input, where power is torque into omega. So F into R, this is the torque, and omega is 2 pi n. When we represent it in this form, we get dg ng by dw nw, which happens to be tan of lambda. And so efficiency is the tangential force at the gear upon tangential force at the worm multiplied by tan lambda. So Tg at gear is same as Ft at gear is same as Fa at worm. This we have discussed, and we have also derived the expression for the Fa by Ft for worm, which happens to be like this. So we are rearranging the expression to get the formula for efficiency as cos theta into mu tan lambda upon cos theta plus mu tan lambda. From the cube that we have drawn for Fa, Ft, Fn and Fr, you can get this expression of theta. Tan theta will be tan phi n, where phi n the pressure angle into cos lambda. So these formulas we'll be using in the next class, and we'll design worm and worm wheel in Tuesday's lecture. So that's all from my end. Do you have any questions to ask? Please feel free. Anybody has any questions? Ujjwal Kumar, Anshuman?
No doubts, ma'am.
No doubts. Sahil? No. Okay. Well, thank you. We'll stop here.